subatomic particle at a radioactive material. Radioactive means it's unstable. It's always trying to get rid of some of its parts. And we help it along a little bit by firing a neutron, which is a subatomic particle, into this uranium, which splits it. And when it splits, it throws out more neutrons, these little subatomic particles, releases a large amount of energy. If those two are hit, they split again. And it sets up all these other neutrons go off and hit other atoms of uranium, and it sets up what's called a chain reaction. When I was a kid, man, they talked about chain reactions. We didn't have any idea what they were, but it was cool in the old Rocket Rangers movies and stuff. I was a Rocket Ranger when I was a kid. He sent away a thing in so many box tops, and he got a badge and a helmet. Really neat. Spaceman. Of course, that was long before we'd even shot a little satellite up in space, much less people. So in fission, nuclear energy is released when we split atoms apart. And when you split them apart, they form a different substance. Because the only thing that makes one substance different than another is how many of these subatomic and electron particles that are related to a particular substance. Helium is the simplest, by the way. One proton, one electron. That's it. No neutrons. Fusion is when energy is released when, again, smaller chemicals are fused together and form a new one. And there's always an excess amount of neutrons and energy that's released during that process. This is the way the sun works. The sun is primarily hydrogen. And through the heat and the pressure in a huge star like that, now, I shouldn't say a huge star. The sun is a moderate-sized star. It's not a big star. It's not a little one either. It's just right. It's like Goldilocks and porridge, you know. If it wasn't just right, we wouldn't be here. You start thinking about what the absolute miracle of all the things that have come together to make Earth support life as we know it. It's just really incredible. And there's all different people interpret that in different ways, and I respect all of them. But through the process of fusion, hydrogen becomes helium. We know what helium is. Breathe some air, you talk like this. You know, that's about all most of us know. That makes balloons float. The Germans found out in the 30s that hydrogen, even though it was a wonderful gas to put in balloons, big balloons, dirigibles, they pumped the Hindenburg full of hydrogen across the Atlantic, and when it tried to land in the United States, it blew up. And one of the most famous disasters as far as, and it was being broadcast over the radio, and the radio announcer just lost his composure altogether. Just kept saying, the humanity, the humanity. But you could see people jumping out of this thing, and I mean, it was about like 9/11. But hydrogen fuses to form helium, which is the second simplest type of element. And that's why it floats. It's very light, it's very buoyant. And this process is what produces all the energy that we utilize from the sun. And of course, we only get a little piece of it. The rest of it goes out in all directions. And you know, the sun's going to use up all that hydrogen. Probably, they say, within 8 billion years. So you've got to be prepared for that. Now we got to wait for that. Now atoms. Basically, we have a nucleus, and we have what aren't really particles. They don't know what an electron is exactly. And it behaves as a particle. It also behaves as a wavelength. So we just call it a bundle of energy. Matter and energy are actually the same thing. It's just how concentrated they are. That's hard to comprehend, but it's true. So we have a proton, which has a positive electrical We have a neutron which has the same mass, the same weight as a proton, but it doesn't have any electrical charge, it's just neutral. It's kind of lost. If it ever had a charge, it's lost it, so it's neutral. And we have, collectively, the protons and the neutrons in a substance are called the nucleus. This is where all the weight is. I heard back when I was young, and this impressed me, they said if you could condense all the empty space out of an atom, in other words, essentially squash the electrons down to the nucleus, that every bit of matter in the universe could be held in a tablespoon. But it would have the same mass as every bit of the matter that's in the universe. Of course, if it was every bit, you wouldn't have a tablespoon, which it would be part of it. I don't know where people get this stuff. I just report what I hear. And again, these electrons are what give atoms their character, in that they're always trying to either take in another atom's electrons or give up their own. And those that try to give them up merge with those that are trying to take them in. And so we have combinations of atoms such as CO2, carbon and two oxygens chemically combined from this process of sharing electrons. So we're not getting into that. If you had chemistry, you know all about that. If you had physics, you know. Now, I used to make people understand about all the atomic number and the atomic weight and all that stuff. It's really not important when you're talking about, it's important, but it's not essential when you're talking about how nuclear processes work. Some of these radioactive atoms become really complicated. They have large numbers of protons and neutrons and electrons in different energy levels that they don't rotate like a planet does around a sun. It's like a basketball around a basketball around a basketball, and that whole area is an energy level. So the ones that we call radioactive can be in different forms, and it's based on how many total particles are in the nucleus. And those that have an unbalanced number of electrons and protons tend to be unstable, and those that have a balanced number are stable. So we have stable forms of uranium, and we have unstable forms, like this one. This one has an atomic mass, to add up the protons and neutrons, of 38. There's also 238. There's also 238 electrons. But in U-235, it's unstable. You have 3 fewer neutrons. So it's always trying to break down and change into something else. So when we do fission, we just help it along. Now it's hard to picture how we accelerate a neutron into a radioactive atom. But that's done through a cyclotron, which is as big as a football field in some cases. But they can accelerate subatomic particles, hit a radioactive particle, and it causes an unstable condition and breaks into different substances, krypton and barium. That's what U-236, which is another unstable form, actually does. Now, when that happens, it spits out 2 neutrons and releases a large amount of energy. These go on and split even further. There's another way of looking at it. Only this one's splitting into krypton and barium. Well, that one is too. This is the same thing, just a different picture. Sometimes they split into something slightly different. But what makes this whole process work, that is in nanoseconds, one electron fired into one atom can cause a chain reaction that can happen in a heartbeat. Well, that's the heartbeat. In fractions of a second. And so large amounts of energy are released. And that energy, if controlled,